Welcome to Lecture 8A, entitled Small Signal Modeling Framework. We had discussed earlier when we discussed tangent planes, different ways in which tangent plane could be basically interpreted, and one of them was basically when we're dealing with dynamic equations, and we're interested in small signal behavior. So in this particular lecture, we're just going to look at the framework for setting up the problem, and in Lecture 8B, we'll actually go through a worked out example of a problem. So the material for this lecture comes from Reading Assignment 2, Introduction, and Section 2.1. And as I stated, the objectives are introduce a framework for determining the time evolution of a dynamic system consisting of state variables, inputs, and outputs for small perturbations about a DC equilibrium operating point. The concepts and definitions coming out of this teaching module are: what is a Jacobian matrix, and what are state-based equations, output equations, which consist of state variables, input variables, and output variables. As usual, the second slide is just a summary of the slides that I will be presenting in this presentation, so I'll just move on to the next slide. Okay. Question is, where is small signal useful and where is it employed? So I'm giving you just two specific examples, but it's used in other places as well. So for example, if we want to develop insight about the behavior of a system for which a physical model exists, may not exist, or is primitive. For instance, if we want to model transistor behavior when used as an amplifier, or we want to model electrochemical cells and understand how they behave, or perhaps improve in terms of designing better models, then small signal modeling is helpful. On the other end, we may want to investigate the stability of a physical model about an operating point so that a controller that delivers robust regulation and tracking performance can be designed. Just to make a note here that small signal modeling is an important topic in ECE 231, which you'll be taking next term. All right, so the first thing is to define what we call a Jacobian matrix, which we'll be using extensively throughout the course. But there are just 2 points to keep in mind here, and that is, first of all, that Taylor series approximation of one or more functions to first order that we'll be looking at means that we retain terms involving only first order derivatives. And second is the thing what we call transformation of variables. And this involves something called the Jacobian matrix. What it does, it relates the partial derivatives of the old variables with respect to new variables. And so if a transformation is required, and it's this Jacobian matrix that makes the connection between the two variables. So for example, on the left, we have transformations involving single variable, two variables, three variables. And on the right, the Jacobian matrix. So in the case of a single variable, a Jacobian matrix would be just df by du. And so df du here would be a 1-by-1 matrix, but that's equivalent to a scalar. And this is something that you basically looked at last year when you were doing integration. Right? You basically made a substitution of variables and basically required a derivative in the calculation process. It gets more interesting when you start dealing with two variables. So for instance, if we define x in terms of two new variables through a function f of u of v and y through a function g u of v, then we set up the partial derivatives in row format. So for instance, if we take the partial of f with respect to u, partial with respect to v, which would be the first row, then partial g with respect to u, partial g with respect to v, second row, that forms a 2-by-2 matrix. And that 2-by-2 matrix we call a Jacobian matrix. That's just the name that's given to it. We can write it in matrix form or in short form. We basically can show this as just being this sort of squiggly d xy, squiggly d uv. This and this are basically equivalent. If we're dealing with three-variable system, which would be this case here, then x would be a function of uvw, y is a function of uvw, and z would be a function of uvw. And so in this case, we would be taking the partial derivative with respect to u, v, and w for x, y, and z. So we go row by row. This is the F row with F partial derivatives, the row with G partial derivatives, and the row with H partial derivatives. So this would be a 3 by 3 Jacobian matrix, and this is an equivalent way of writing it in short form. So this is what we call a Jacobian matrix, and how it's to be used will become evident as we move a little bit further into the course. All right, so to be specific, where are Jacobian matrices used? Well, we use them to solve nonlinear equations, and there is a discussion of this in section 1 of reading assignment 2. You're not responsible for the material, but nevertheless, you might be interested in looking at it if you ever got time, because the matrices are used to solve nonlinear equations. Small signal modeling, which is section 2 of reading assignment 2. This material you'll be responsible for and is the subject of this lecture and the following lecture. Third, transformation of variables for multivariable integration, which we'll be looking at later in the course, not too much longer. And this is from section 3 of reading assignment 2. You'll be responsible for looking at it, only the introductory portions. Transformation of coordinates for vector operators. This is from section 4 of reading assignment 2. You're not going to be responsible for this material, but the idea here is to show you the number of ways in which the Jacobian matrix sort of is utilized or appears. All right, so now let's go back to reviewing something we had dealt with when we discussed tangent planes. And so this is the notion of state-space equations and output equations. So what I've shown here is a box. In that box are, we call the state variables x1 through xn, as many as is required. You have input variables up to m, again, depending on how many are required, and outputs, which go from 1 to k, again, as many as is required. Now, the system in the box basically is the system that models your whatever it is that you're looking at. So, for instance, it could be some circuit equations involving capacitors and inductors. And so the state variables would represent basically the components that are associated with energy storage. So L's and C's, for example. Again, we'll show this through a demonstration in the next lecture. All right, so how do we typically write these things in equation form so that eventually we can solve them? So if you look at on the left here, these are what we call the state space equations. And in this case, what we have are 2 state variables and 2 input variables. The 2 state variables are the ones associated with the derivative terms. So there are 2 derivatives. So you have an x1 and an x2. So that means n would be equal to 2 state variables. And these are functions of x1, x2, the 2 state variables. U1 input variable, U2 input variable. In this case, there are 2 input variables. So it could be function of both of them, one of them, maybe none of them. And for the second state variable, the derivative x2 with respect to t would be a different function of the state variables x1, x2, input variables u1, u2. You also have the output equations, which would be typically involving the 2 state variables and the 2 input variables. So you might have 2 outputs, you might only have 1 output. I've just basically shown an example with 2 outputs. So this is an important note here at the bottom. When developing state space equations to a model system, because that effectively is the task, is to create system equations to make them compatible with a set of state-based equations. You only want 1 derivative to appear in each state-based equation, and it turns out not every input or state variable needs to appear on the right-hand side of each state space equation. Every system will look different. Okay, so let's look at example of a state space equation, output equations for a 2 state variable, 2 input, and 2 output linear system. So linear means it would be linear in the input variables, linear in the state space variables. That's what linear means. So on the left here are your state space equations. You notice in this case, I basically have all input variables and all state variables included on the right-hand side. So this is basically 2 state space equations. Now, in a linear system, we can write it either in this form, in functional form, or we can write it in matrix form. So for instance, the same set of equations could be written in this form. If you multiply this matrix out by this column, you'll end up basically with the two equations involving just the state variables. If you then basically multiply these B matrix times U1, U2, you'll basically obtain the remaining terms here, the remaining four terms. So all of this basically, we can basically define it as a matrix A, and this we can define as some matrix B. All right, so this would be the case when we're dealing with a linear system. Output equations here in this case also are linear. State variables are linear, input variables linear. We can then represent this also in terms of matrices. So this would be the matrices involving the C terms associated with the state variables. And then we have matrices involving D values that's associated with the input variables. And again, this can be just represented by matrix C and this by matrix D. So this is sort of generally how you would set the problem up. Now we can also have a nonlinear system. In this case, for example, we'd have two state variables, two input and two output nonlinear system, and a two output nonlinear system. So if we look at this set of equations now, here are our state-based equations, but this now is not linear in x1. So we have one term here which is nonlinear. And if we look at the output equations, this one's linear, but this one's not because it involves the fourth power of one of the input variables. So in this case, basically, it's nonlinear, and we would not be able to write either this set of equations or this set of equations in a matrix form. It's only the case if you're dealing with linear systems. All right, so state-space equations and output equations are nonlinear, at least one state variable or one input variable. And nonlinear equations, as I said, cannot be represented in matrix form. All right, so now basically we're looking at the process for small signal modeling about what we call an operating point. So what do we mean by small signal inputs? So that just means you take the input signal and you perturb it about a specific DC value, constant value. So here, for instance, you have U1 as a function of t is a steady state or DC value plus a perturbation, which is a function of t. UT looks the same. So these U1, U2 in bold basically are our constant input signals. Okay, so the input signals are typically a given. It's a given, right? U12 and U22 hat are small input perturbations, and as a function of about time, about the operating points U1 and U2 respectively. Okay, so the next thing is to look at the state variables and the output variables. So for perturbations in the input signals, we will cause the state variables to change and the output variables to change. So that means, for instance, if you look here, one of the state variables will now be defined based on what its steady state value was plus a perturbed value. The other state variable would be equal to what the steady state value was plus the perturbed value. And the y1 and y2 values will involve the steady state values, y1 and y2, plus the perturbed values. x10 and x20 are referred to as the state variable operating points, and capital Y1 and capital Y2 are referred to as the output variable operating points. So this is our starting point. So now what we do is we take these equations, this one, this one, this one, and this one, right? And this one and this one, and substitute them back into our original state-space equations. So the derivative term now, this is x10 plus x1 hat. This is a DC term. If you take derivative of this term is 0, and you're just left with this term. Here, we just replace x1, x2, u1, u2 by the perturbed values from the operating point. So you can see these are just the perturbed values. Similarly, for the second state variable, the derivative with respect to a constant value is 0, so you're just left with dx2 hat divided by dt. And again, here are the perturbed values for the state variable x1, x2, u1, and u2. Similarly, for the output variable, we would have the DC value, the steady state, plus a perturbed value of y, is g1s of some function. And again, these are the perturbed values of x1, x2, u1, and u2. Similarly, for the second output variable, y2, this is a perturbed value, and this basically would be the perturbed value of x, y, x1, x2, u1, and u2. So the objective is going to be to determine the operating points, right, and small signal perturbations for the state variables and output variables. Input variables are a given, so we don't have to do anything there, but we need to determine the operating points for the state variables as well as the output variables before we can basically look at the small signal behavior. So that concludes Lecture 8A. Thank you for listening.